Okay, the last topic in Chapter 1, so hopefully you've been preparing for that first test, because this is the last topic for Chapter 1. The last thing we're going to talk about is average rate of change, and then the difference quotient, which is a special expression of average rate of change. Right, average rate of change is a very important topic in higher level mathematics, college algebra and beyond. And so to get you to kind of understand what it is, I'm going to look at a very simple example, because it's just easy to understand distance and time, right? You have a distance and time formula. And so suppose that you traveled 110 miles in 2 hours. And so what I want to know, what was your average rate of change, right, for your trip? What was the average speed for your trip? And so the average rate of change in this case would be the change in distance over the change in time, if you can read that. So change in distance over time. So the distance we went is 110 miles. It took us the change in time of 2 hours. Divide that out, it's 55 miles per hour, which is a speed, right? That's how fast you traveled on average. It didn't mean that you stayed 55 miles. You could have, but that's not what it means. It means that's what you averaged. Sometimes in your trip you might have been going more than 55 miles an hour. Sometimes on your trip you might have gone less than 55 miles per hour. Sometimes you might have gone 55. But over the entire trip, that was your average. Your speed averaged out to 55 miles per hour. So again, you might have had different speeds during the 2 hours. You added them all up and found your average. The average is 55 miles per hour. Right? So that's what average is. And so the average rate of change formula. All right, average rate of change formula generically for a function. All right, suppose I have 2 points that I know. All right, two distinct points on a graph. The average rate of change of my function from point 1 to point 2, so from my x value 1 to my x value 2, is found the following. So average rate. Well, it's the change in my function over those values, so it'd be f of x2 minus f of x1 over x2 minus x1. Or another way to think about it is, this would be a y value at 2, so that would be y2. This would be a y value at x1. And so it's the change in my y values, my function values, over the change in x. That should look very familiar to you. Right? Just like our change in distance over change in time, right? Distance would have been the function, right? We're traveling a distance. Time would have been the x value, right? The independent variable. And so time changed by 2 hours, distance changed by 110, average rate was 5 miles per hour. Well, in general, that's what we do. We find the change in the function value divided by the change in the input value, the x value. That change, when we divide it out, gives me my average rate of change. That should look familiar to you, right? That's a slope. Right? The average rate of change equals the slope of a line passing through those points. Right? What it is, it's a special kind of line called a secant line, so graphically, if we graph it. Alright, so I'm going to draw a function that's nonlinear. There's my x-axis, there's my y-axis. Alright, so suppose this is my nonlinear function f of x. I graph 2 points, so suppose I pick a point here, so there's my x1, and I pick a point over here, there's my x2. Alright, connect the dots, so I'm going to draw a red line, it's supposed to go through my dots. There's the line that passes through those 2 points. Alright, it's a secant line. Alright, passes through the point x2, f of x2, and passes through the point x1, f of x1. And so what it is the slope of that line equals the average rate of change for f of x from x1 to x2. And so this particular function, just based on the picture, it looks like on average the function's increasing, right? And whatever that number would be, so if n came out 2, well, the function on average is increasing by 2. Well, and it's just an average, so if you look at it, it actually decreases a little bit here, and then it gets steeper as I move on. It's not so steep here. And so if you look at it, it actually is different speeds, different slopes, right? I might have negative slopes here, small slopes here. Somewhere I might reach a 2 slope. Right? But this is adding up all my negative slopes and all my positive slopes. When I add up all my slopes between the first point and the second point, it averages out to whatever that m value is, whatever the slope of that red line is. That's on average how much my function increased between those two moments. It's the average rate of increase, the average slope over those moments. Alright, so we're just going to practice finding that. That's the first one. Find the average rate of change from x1 to x2. Alright, average rate of change, so my function, is 2x minus x squared. I want the average rate of change from 1 to 3. Alright, so I'm looking for the average rate of change. Alright, so it'd be change in the function value, so f of 3 minus f of 1 all over 3 minus 1. Again, you have to be consistent. If I plug 3 in to get, these are y values, this would be y2. This would be y1. Alright, so to find those, you have to plug them in here. Alright, so to get f of 3, I have to plug it into my 2 times x squared. So 3, so I would take this and take 2 times 3x squared. And subtract 2 times 1 squared all over, I could do 3 minus 1, which is 2. Alright, so to simplify up top would simplify to 9 times 2, which is 18, minus 2, all over 2. 18 minus 2 is 16, divided by 2, and so 8 is my answer. F of x has an average rate of change of 8, so it's increasing, I know that much, and it is increasing pretty fast, right? 8's a fairly big number, it's not a huge number, it's bigger than like 1 or 2, and so I know my function, f of x, is increasing by 8 units per x value on average between 1 and 3. Alright, so just between those, if I pick different values, I'd get a different answer. So between x equals 1 and x equals 3, the function's increasing on average by 8. Now, at different parts of it, it might be increasing faster, slower, I don't know, but all I know is the average is 8. Alright, so I'm going to do more examples, and I might relate them to the graphs too, just so you can see how they relate graphically. Alright, so first example, f of x is equal to the square root of 2x minus 1. Find the average rate of change, so ARC, average rate of change, from x equals 1 to x equals 3. Alright, so that means I'm going to plug 1 and 3 in. So my average rate of change would be f of 3 minus f of 1 all over 3 minus 1. Again, I plug my 3 and 1 into my function. I'm just going to do the math in my head. So first thing I'm going to do is I'm going to plug 3 in. So it's going to be 2 times 3, which is 6, minus 1, which is 5. So I get square root of 5 for the first one, for f of 3. F of 1 would be 2 times 1, which is 2, minus 1, so that's 1, so it's square root of 1, all over 2. And so I have square root of 5 minus 1 over 2, and I'm just going to find the approximate. Right, that's exactly what the average rate of change is, and so I'm going to type that in the calculator. So be careful. Make sure if you type it in the calculator, you put parentheses around the square root of 5 minus 1, because that's what the order of operation you have to do first. And then once you do that, then you divide by 2. So make sure you put a parentheses there. And so when I do that, what's the average rate of change? The average rate of change comes out to 0.618 if I round 3 decimal places. So it's growing, on average, by 0.618 units per change in x between 1 and 3. Let's do a second example. Alright, so f of x equals negative 8x plus 5. Alright, this one's a little tricky. Tricky is the wrong way to word it. This one, students will overthink. Alright, find the average rate of change, so the ARC, from x equals 0 to x equals 1. So I'm going to find f of 1 minus f of 0 all over 1 minus 0. Alright, so first thing I plug 1 in, so I get negative 8 times 1 plus 5. It's going to come out negative 4, right? Negative 8 times 1 is negative 8 plus 5. Oops, not negative 4, negative 3. Alright, minus, when I plug 0 in, that's going to 0 away. I'm going to get a 5 out, so it's minus 5, right? 5 is the number that comes out. F of 0 is 5. All over 1, so 3 minus 5 is going to leave me with negative 8 over 1, so my average rate of change is negative 8, which is the same as the slope, so it should make sense. Remember, what makes linear functions unique is their rate of change is constant, which means all rates of change are negative 8, and so all average rates of change are negative 8, because all my slopes are negative 8, so when I average negative 8, it's going to come out negative 8. And so that's always going to happen with lines. Whenever I have a line, I'm finding average rate of change, it's equal to slope. Always. Always equal to slope. Alright, so we're going to stop there. And so the last thing, so the last video is going to be on the difference quotient. And the hardest part about the difference quotient is simplifying it. And so that's the last video. Right? It's a special type of average rate of change.